Everyone, thank you for listening to my talk today. The talk is about optimal mixed discrete continuous planning for linear hybrid systems. This is a joint work with Brown Williams and Chu Fang. Hybrid planning is a problem of planning valid control commands for hybrid systems to achieve user-specified specifications. Here, hybrid means the system has both discrete modes and continuous dynamics, which are represented by discrete and continuous variables. These variables can change instantaneously or continuously under different modes. In this paper, we specifically consider linear dynamics, in which the dynamics function are linear functions of control variables. So the system here is called linear hybrid system. In order to motivate the problem we focus on in this paper, I'm going to introduce a pedagogical example. Here, we are using a transportation example on Mars. Consider on Mars, an astronaut should go to an observation location by crossing different terrains such as mountain, ground, and basin. A rover needs to go to the charge station. The astronaut can either walk or take a rover. The moving speed of the rover is much faster than the walking speed of the astronaut. The rover is powered by a battery, which can be charged in a charge station. In different terrains, the rover has different speed limits and energy consumption rates. As we can see here, a fast plan is rover gives astronaut a ride because it can move much faster. As the battery is not enough, the rover needs to go to a charge station for charging first. The problem is hybrid because astronaut can be in the mode walking or taking a ride, and the rover has different modes in different terrains. As we can see here, the astronaut needs help to get the destination sooner from the rover, so the subsystems here are coupled and the coordination is very important. In addition, the continuous dynamics are also different under different modes. For example, the rover moves slower and consumes more energy when moving in mountains than moving on ground. Additional factors such as resources should also be considered here to make sure the rover is not drained along the way. As we always want to find high-quality solutions, the problem can become much more challenging. Here, I summarize the difficulties of solving these hybrid planning problems as 4 factors. First, only considering discrete mode transitions is p-space complete. In our example, we have 2 modes, walking and riding for astronaut, and 4 modes for rovers. So there are 8 modes in total. If we consider n steps, there are 8 to n different plans. Second, only considering numbers in planning is undecidable in theory, which means there does not exist a complete planner. Now to see, we have to consider underlying dynamics. Third, resources such as batteries are involved in this problem, which makes the problem much more constrained. So we have to carefully reason over resources and make decisions to refuse them when it's necessary. Last but not least, we have a favor of high-quality solutions with minimized total time or energy consumption, which is much harder than finding a valid solution. A lot of real-world applications require such planning capability. This kind of hybrid nature can be also seen in planning underwater vehicle exploration, truck and drone collaboration to deliver packages, and air refueling for exploration tasks. In terms of related work for hybrid planning, we have discrete abstraction-based synthesis algorithms, which focus on solving control synthesis problems with complex nonlinear dynamics, stochastic uncertainties, or even non-deterministic transitions. However, these methods suffer from the scalability issues by discretizing the high-dimensional state space. Also, they only focus on finding valid solutions instead of high-quality ones. Another line of research is based on sampling methods. In addition to traditional RRT, PRM, and FMT, some hybrid automata planner can solve similar problems with both discrete and continuous specifications. However, they only provide asymptotically completeness guarantees. And PDL is the most representative planning formulation. Hybrid PDL planning has been a popular topic in the past decade, which focuses on planning for general models with both discrete states and continuous dynamics. Built upon the success of PDL planning, researchers have developed powerful planners with richer features from number, time, continuous linear effects, or dynamics. In this category, PDLS is most to our interests because it solves problems with control variables, which makes the approaches much more applicable for robotic scenarios. As planning for such a problem is hard, most of these methods get scalability by using greedy search method with the help of heuristics, which is incomplete and can get arbitrarily low-quality solutions, especially when resources are considered. MUP or SMT-based methods are complete and optimal, but they often discretize the timeline and can only scale to short horizon problems. In this slide, I will discuss two PDL planning approaches called Scotty and Commin, which are most related to our work. First, Commin is the first PDLS planner. The idea of Commin is to directly discretize the timeline and encode the hybrid flow graph as a MUP. As this encoding has all the valid plans, Commin is complete and optimal. However, Commin is not scalable since a long horizon plan might have hundreds of time steps, which leads to a very large-scale MUP. Another planner, Scotty, uses a relaxed hybrid graph plan to compute the heuristic and employ a graded heuristic search, which are similar to many other temporal planners and classical planners. It avoids a timeline discretization by giving each action an adaptive duration, so it's much more efficient than Commin. However, its graded search is incomplete and always falls into blind search in our experiments, especially when resources are involved. Our approach uses the MUP encoding as Commin, so it can be complete and optimal, even if the resource constraints are involved. We also avoid the timeline discretization by encoding the action duration as a variable like Scotty, so it typically only needs a few steps to plan a long horizon problem. This slide provides a graphical example of the high-level modes and their discrete transitions of our motivating example. As we can see, astronaut can walk or take a ride. The rover can stop, charge, or drive in different terrains. The actual model we are using is a hybrid automata model, which adds dynamics to the symbolic model. A hybrid automata model consists of 6 parts, which are discrete state variables, continuous state variables, control variables, initial and goal states, jumps, and flows. Consider our motivating example. The discrete state variables are the modes of astronaut and rover. The continuous variables has astronaut position, rover battery, and rover clock. The control variables can be discrete or continuous. The discrete commands are used to switch between different modes, and both agents have velocity as control variables. And we also have initial and goal state. For jumps, it has a condition, which is a constraint that must hold when this jump is active, and effects, which means how states are changed after a jump happens. For example, when the astronaut is walking and the rover and astronaut are at the same place, the astronaut can board on the rover, and astronaut mode is changed to riding. Flows also have conditions, which should hold during all of its active period, and it's associated with a dynamic function, which specifies how continuous variables are changed. Here, if astronaut is riding, the position change should respect the rover velocity. The solution to our planning problem of a linear hybrid automata is an input command, which specifies the control values over time. An input command is valid if there is a corresponding valid run. A run is an interleaving sequence of states and action time pair. Action is a jump or a set of flows. Here, delta is the elapsed time of this action. A run is valid if it satisfies two requirements. First, the first state should be the initial state and the last state satisfies the goal. Second, for each action, if it's a jump, it should have zero duration. The jump condition should be satisfied by the last state, and the next state should respect the jump effect. For set of flows, the condition should hold for the whole duration except the end of this action. The continuous variables should respect the dynamics and the given input command. In addition, the discrete state variable should remain the same. In this planning problem, we consider an objective of minimizing the total time. Okay, now I'm going to introduce how to encode such planning problems as the MUP, which basically capture all the valid input commands and runs. I will first introduce the variables here, and then all the constraints with respect to our problem definition. Assume our run has fixed time step n. We have n+1 states and n actions in total. Note that if a solution has less than n steps, it can be also captured by our encoding because we can have dummy flows with zero durations. First, we have three different MUP variables at the start and end of each step to represent the states. For each state, we have discrete state variables, continuous state variables, and input variables. They are L, X, and E here. And we also have different three variables at each step to represent the action and their effects. First, for each action, we use a set of Boolean variables to represent the activation of operator, each of which is defined for a jump or flow. A jump or flow is activated if its Boolean variable is 1. It's not activated if it's 0. Also, action has a continuous variable for its elapsed time. Meanwhile, we have a set of continuous variables to represent the cumulative effects of input variables. This effect is basically the integral of the input values during the action. By doing this, we can have an adaptive continuous duration for each action without worrying about the actual integral operation. This cumulative effect encoding is a key idea of flow tube in Scotty, and it's very important for our approach to support long horizon planning. We have 10 constraints to make sure the solutions are valid for our planning problem. They can be classified into 4 categories. The first is for the initial and goal state constraints. The second class is to enforce there is only one activated action at each step. The other 2 categories encode the conditions and effects of the activated jumps and flows. So I will just skip the first category because it's trivial. As initial, so the activation constraint enforces either of these 2 conditions hold. One jump is activated, or the dynamic functions of all the activated flows exactly cover all the continuous variables. For example here, we have 2 activation constraints for our motivating example. Recall that an operator is activated if its Boolean variable is 1. The first is that the sum of all the jumps and all the flows for astronaut should be exactly 1, and same for the rovers. As we can see here, if a jump is activated, all the other jumps and flows should be inactivated. On the other hand, if an astronaut flow is activated, all the jumps should be inactivated, and there should be exactly 1 activated rover flow as well. When a jump is activated, its condition and effects should be respected, and its duration should be 0. As our automata is a linear automata, all the conditions and effects are in the form of linear constraint formulas, which are linear constraints joined by conjunction and disjunction. As a constraint in a MUP can only be conjunctions, we need to compile away all the conditional relations which are implications as well as the disjunction. So we use the big M method to do that. Now let's move on to the flow constraint. When a flow is activated, its condition should hold during the whole interval, and the continuous state evolution should respect its dynamic functions while the discrete state variables remain the same. The condition constraint here is similar to the jump condition. I will show how to encode the linear dynamic effects when the input variables are constrained by flow conditions, which are constraint 8 and 9. As there are conditions on input variables during a flow, they should be considered when describing the possible state evolution. We encode the flow condition on input variables during a flow as the constraints on cumulative effect variables, which basically integrates the linear constraint of input variables E and get a linear constraint of cumulative effects and elapsed time, which are delta, big delta and small delta. Here is an example. When rover is traversing a mountain, its velocity limit is 2. After simply integrated, we obtain the constraint on the right. This basically says the effect of the rover velocity should not be larger than 2 times the elapsed duration. With these constant cumulative effects, we can describe the state evolution. The idea is also integrating the dynamic function on both sides. For example, when an astronaut is on the rover, its position changes with respect to the rover velocity, so its position after this flow is basically the previous position plus rover velocity cumulative effects. So far, we have sketched the variables and constraints in our MUP encoding. In fact, we also have 2 classes of constraints that are redundant but can speed up the solving procedure. The first class is a mutual exclusion, when 2 flows cannot happen together given their exclusive flow conditions. We add redundant constraints to prevent them from happening together. The second class is the subsequent conflicts, when one operator's possible end states and the other operator's possible start states are exclusive. We prevent them from happening in sequence. These ideas are quite similar to the mutex in classical graph plans, which can help the solver to quickly prune a large portion of infeasible solutions. Okay, the last but not least, our MUP planning framework can also handle temporal concurrent goals represented by QSP, a qualitative state plan. The key idea here is we can translate QSP to a linear hybrid automata and compose it with original automata. The main ideas are as follows. First, we define a continuous clock variable for each episode to record the elapsed time and the activation state during each episode. Then, we define a jump for each event. The jump condition are all the temporal constraints of its ending episodes, and the effects reset all the clock variables. Third, we put the episode state constraints into the condition of a flow, and the clock variable has a change rate 1 in its flow dynamics. As long as all these jumps and flows happen exactly once, our solution can satisfy the QSP specification. We benchmark our planner against Scotty, which is the state-of-the-art hybrid planner, on 3 challenging domains. All these domains feature multiple agents with hybrid specifications and renewable resources. We set a runtime limit to 600 seconds and report both the first solution and incumbent solution after 600 seconds. The experiment's results show that our approach can find the first solution around 1 second, and Scotty fills half of the problems. Our first solution is already better than Scotty and can be further improved in the rest of the runtime. Our approach can prove the optimality by exhausting the solution space for most cases within runtime. The first domain is the same problem as our motivating example. Here, an astronaut should go to a destination and a rover can pick and deliver the astronaut. There is a charge station where the rover can recharge. The terrains include mountain, ground, and basin. We test 4 instances. In the first instance, the rover has enough battery and does not need to charge, so the rover can directly pick the astronaut and deliver it to the destination. In the second instance, the rover does not even have enough battery to go to a charge station, so the astronaut has to walk from the middle. In the other instances, the rover has enough battery to go to a charge station, but not enough for the whole trip, so they charge along the way for delivery. This table shows runtime and solution qualities for both Scotty and our MILP encoding. The blue boxes give the finally returned solution runtime and objectives. A red box shows those of first solutions, and the green box shows the runtime to first find the optimal solution. As Scotty terminates after finding its first solution, its first solutions and the final solutions are the same. As we can see, both Scotty and our planner can find the first solution in 1 second, in which astronaut walks directly to the destination. Our planner further improves it and returns optimal solution in less than 5 seconds for all the problems. The second domain is the air refueling domain, which are borrowed from the Scotty benchmarks. In this domain, UAV needs to take photos at given regions, and there is a tank plan along the way to help refuel. We test on 4 different instances with different numbers of UAVs and regions. If we look at the last instance, in which 2 UAVs complete the photo taking tasks along 2 optimal passes and refuel along the way, this shows our algorithm can indeed plan for optimal solutions with respect to task assignment and passes. As we can see here, Scotty fills the last 2 problems, while the MILP approach solves all the problems very quickly. The last domain is the truck and drone delivery domain. Here, we use both trucks and drones to deliver a package on a transportation network. The network has 5 depots and 10 highways. Trucks can only drive on highways by following the given direction and speed limits. The speed limits can be different on different highways. Drones can stay on trucks or deliver package with slower speed. In our experiment, we benchmark with up to 2 trucks, 4 drones, and 4 packages. Here is an example of the expected good plan. Here, we need to deliver packages on highway. There are 2 trucks, and each truck has 1 drone and 1 package. The packages should be delivered to the opposite of the road. As truck cannot make U-turns on highways, drones are used to switch packages by crossing the roads, which saves a lot of time than switching the packages at the next depot. In the table, we can see Scotty fields solve all the instances, while the MILP encoding can find the first solution in 2 seconds. And it can also further improve all the solutions in the rest of the time. Here, we give the table of all the experimental results. And that's it. Thank you for listening to this talk.